This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So the plan today is to start looking at Nyquist stability analysis. So this is yet another tool for assessing the stability of feedback control systems. But before we start looking at that, I just want to point out a few things from the discussion yesterday around workshop 3. So this is based on some questions that I got at the end of the lecture. So I think maybe at the start of the lecture I misspoke, but when discussing the method for identifying the parameters in the motor model, what you did in the lab was apply step inputs at the voltage, okay? And we would go from plus, minus, plus, and of course the response to that is a ramp-like signal because we have the integrator there. So it's like we're integrating, just a constant. And if you integrate a constant, you get a straight line. So V looks like that in the experiments we're doing, and the response was something that was pretty close to a ramp, but of course it curved around at the corners because of this pole here. Okay. I think there was a squared missing there. When expanding that, and at the end we noticed that by using feedback control we could achieve our objective of tracking a ramp reference with small error, and that error could be made arbitrarily small by just making the controller gain K very large, okay? But you may not want to make the controller gain too large, right? So if we look at the root locus plot for that feedback control system, we've got an open loop pole at the origin, and we've got one at -1 on Tm, okay, and we've just got a proportional gain controller. So the closed loop poles, were the zeros of this rational function. Okay, so as we increase k from 0 up to positive infinity, or for small k, we're going to get two zeros of this rational function. The zeros of this rational function are the closed loop poles close to the open loop poles. And as we increase k, this one moves this way, this one moves this way, okay, and eventually they meet. And when they meet, they split apart. And one goes up this way and one goes down this way. So as we continue to increase k, right, this one moves this way, this one moves this way. When they meet, they split apart, one goes up, and as we keep increasing k, it moves further and further up this line, okay, and the other one moves further and further down this line. So while increasing k reduces the error with which we're tracking the ramp reference, increasing k also increases the frequency of the oscillations in the transient part of the response. All right, so if you don't want a lot of oscillations in the transient part of the response, and we'll get a transient bit of the response, whenever we're changing the direction for the reference, right, whether it's a ramp up or a ramp down, we'll always get a transient. And if for a large k, you'll get lots of oscillations in the transient part as it's turning a corner like this. All right, so there's a trade-off. That's an example of a trade-off where increasing the gain improves one thing, it improves the steady state error, but it makes the transient part of the response worse, in the sense that you get lots of oscillations in the transient part of the response before you reach steady state. Okay, so I just wanted to point out that trade-off because somebody asked about it at the end of the lecture yesterday. All right, are there any questions on this stuff, on Workshop 3? So you'll finish Workshop 3 next week. All right, next week you'll have to demonstrate your robot working. Okay, and so in the last hour of the workshop class, the demonstrator will be wandering around asking you to demonstrate your robot, and they'll ask each group member a question to try to gauge, to what extent that group member has participated in designing the controller. Okay? And then you hand in your report in week 10. All right? The demonstrators will give you more instructions on that during the classes next week. All right. So the plan today is to look at the so-called Nyquist stability criterion. So the stability criterion is based on a graphical method, okay, that involves a polar plot of the so-called open loop transfer function evaluated along the imaginary axis. Okay? And the criterion is based on an important result from complex analysis called Cauchy's principle of the argument. So what we're going to do now is try to build an understanding of what Cauchy's principle of the argument is first, and then we will apply Cauchy's principle of the argument to develop the Nyquist stability criterion. All right. So Cauchy's principle of the argument allows you to determine the difference between the number of zeros and the number of poles of a rational function in a closed region of the complex plane. All right. So how we'll apply that to assess the stability of a closed loop will come in a minute, all right? But let's see how Cauchy's principle of the argument works, right? So let's take a closed region in the complex plane, the inside of this red circle. Okay, so it's a closed region. The boundary of that closed region is this contour. All right, I've just chosen it arbitrarily just to illustrate Cauchy's principle of the argument. And let's look at this rational function. Okay, it's not a proper rational function, but who cares? It doesn't matter at this point. All right, it's a rational function equal to s plus 1. Now, that rational function has a 0 inside this contour. All right, it has a 0 at s equals minus 1. Okay, so it's inside this contour which has a radius of 1.5. Okay, so if we evaluate the rational function as we traverse this contour in a clockwise direction, each point on this contour gets mapped to a new point in the complex plane, all right, under this mapping. So the point minus 1.5 gets mapped to minus 0.5, right? The point 0 plus j 1.5 gets mapped to 1 plus j 1.5. We're just shifting all the points along here to the right by 1, right? That's what adding 1 does. Okay, so this contour is produced by evaluating this function as we traverse this contour, right? So this point gets mapped to 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 this point, and so forth. All right. Now, Cauchy's principle of the argument tells you that we're going to get a net change of phase of this of minus 2 pi radians because there is a 0 of the rational function that produced this curve inside the original contour. All right. If you think about what we're doing when we evaluate this function at points along here, as we've seen before, you can think of that in terms of what this little vector is doing, right, as we move around the contour. All right? And you can see that what happens is that the phase starts off at pi, right? And then when we evaluate it here, it's an angle that's, less than pi, right? And as we keep going around, the angle keeps on decreasing. When we get to this point here, right, the angle of the little vector is 0, right? And as we keep going around, the phase keeps decreasing and we get to minus pi. All right, so the net change in phase of this little vector as we traverse this contour is minus 2 pi radians. All right, and that corresponds to, as we're moving around here, so we're following this in a clockwise direction, right? If we follow how the corresponding points move here, we can see that we get one clockwise encirclement of the origin, which is consistent with a net change in phase of minus 2 pi radians. Okay? By contrast, if we change the contour on this side, right, to be such that it does not have the 0 of this function inside it, right, as we evaluate this function at points along here, all right, we get these points, okay? And these points do not encircle the origin, all right? As we go around here, right, which is really just the little vectors that we're getting when we're going around there are just like these little vectors as we're going around here. There's no net change in phase, right? It starts off at 0, then it starts increasing, but then it starts decreasing, right? Keeps decreasing, but then it starts increasing again. And we started off at 0, and we end up at 0, the net change in phase is 0, right? What's the difference between evaluating this function around this contour and around this contour? Well, when we evaluate it around this contour, a 0 of this function lies on the interior, right? Whereas a 0 of this function does not lie on the interior of this. Okay? So what we're really trying to do here is just keep track of the net change in phase. All right? So a clockwise encirclement of a mapping 0, right, contributes a net change in phase of minus 2 pi when we evaluate the rational function along that contour. Okay? So let's say we have a function now that looks like this. That has 2 zeros at minus 1. All right? And if you evaluated this function at points around this contour, right, you get the red contour here, like this. All right? And you can see that the net change in phase as we evaluate this function around here is now minus 4 pi, right? Because we get a net change in phase of the little vector from each of the zeros of minus 2 pi, but there are 2 of them, right? And if we look at the phase of s plus 1 squared, that's just going to be twice, right? So the net change in phase of this will be just twice the net change in phase of s plus 1, all right? And sure enough, if we follow this contour around, right, we've just done one encirclement of the origin, right? And then we get another encirclement of the origin, giving us both in the clockwise direction, right, an encirclement of the origin of the result of mapping points along here under this rational function. In the clockwise direction, it corresponds to a net change in phase of minus 2 pi. So we've got minus 2 pi, and then another minus 2 pi, minus 4 pi. All right? Whereas if we map points along this contour under this rational function, we get this blue curve like this, all right? And you can see that it makes no encirclements of the origin, Right, and sure enough, the net change in phase of the little vectors from here to points on here as we evaluate this function moving along here in a clockwise direction is 0 for both of them. All right, so we'd expect that this would not make a net encirclement of the origin in the clockwise direction. All right, so you can see that by mapping points along a contour to get a new contour and counting the number of encirclements the new contour makes of the origin allows us to determine how many zeros of the function lie inside a region. All right? When we have 2 zeros inside the region that we traverse in a clockwise direction, right, the new contour that we get under the mapping corresponding to the rational function will encircle the origin twice. Right? There's once, and there's another one. All right? This guy, when it keeps on going around like that. All right? Let's consider what happens when we have a pole. Okay, so now the rational function is this, 1 on s plus 1. Okay, so as we map points along this contour, as we traverse it in a clockwise direction, under this rational function, we get a new set of points, right? That new set of points is such that you end up with a curve. While we're moving this way on the original curve, in the new curve, we end up moving this way. Okay? Not surprising, because if we look at the phase of 1 on s plus 1, that's minus the phase of s plus 1. Okay? So when we have a pole of the rational function that we're evaluating along the contour, inside the contour, we get an anti-clockwise encirclement of the origin. Whereas for a 0, we ended up with a clockwise encirclement of the origin. Okay. So as we're going around like this is going around like this, right? Whereas if we map points along a contour that does not contain the pole of the function, then we get, it's still going around in this time in a clockwise direction, but it doesn't encircle the origin, right? And it's because we have no poles inside here, right? So mapping points along a contour under a rational function and then counting the number of encirclements of the origin gives you an indication of how many poles and zeros are inside that original contour. Okay, so let's look at an example where we have a mixture, all right, of poles and zeros of a rational function. Let's consider what happens when we map points along a contour that contains the poles and zeros of the function. All right, again, as we're mapping around here, we get a new curve, right? We're following this around like this, all right? What happens as we're moving around like this moves around like this, okay? And how many encirclements of the origin do we get? We get 1 in the anti-clockwise direction, all right? And the reason we're getting 1 in the anti-clockwise direction is because we have inside this contour, which we've traversed in the clockwise direction, 2 poles and 1 0. All right? That 0 by itself would have given us a clockwise encirclement of the origin. Each of the poles would give you 2 anti-clockwise encirclements of the origin, but altogether we end up with just 1 anti-clockwise encirclement of the origin. Right? When you're looking at the phase of a rational function, right, it's just the sum of the phases. Okay? And what we're doing when we're counting the encirclements of the origin of the curve produced as we evaluate the function along points here is just keeping track of the net change in phase. So the net change in phase due to the zeros will be minus 2 pi. But the net change in phase for each of the poles will be plus 2 pi. Right? And so adding all those things together, we get a net change in phase of plus 2 pi, which is what we can see by counting how many times this curve goes around the origin. All right? So Cauchy's principle of the argument is this, no more, no less, right? And we can use it to determine the excess of zeros of a rational function over the poles of a rational function within a region by mapping points on a contour that has that region as its interior under the rational function and counting the number of clockwise encirclements of the origin made by the new curve that we get. All right? So by convention, we always count clockwise encirclements as positive, right? And anti-clockwise encirclements as negative. All right? So the number of clockwise encirclements we'll get will be Z, the number of zeros of f inside the contour that we traverse in a clockwise direction here, minus p, the number of poles of the rational function inside the contour that we traverse in a clockwise direction. So by just mapping these points to new points in the complex plane, counting how many times it goes around the origin in a clockwise direction, tells us the excess of zeros of the rational function over the number of poles. Right, so the difference between the number of zeros and number of poles. Okay? So that's Cauchy's principle of the argument. How are we going to apply this result to analyse closed loop stability? Well, let's just think about our closed loop. So our closed loop will look like this. Okay. And we've defined the open loop transfer function to be the product of the controller and plant transfer functions. All right. And we have this convention where we represent the controller as a ratio of two polynomials P and L, and G has the ratio of two polynomials B and A. All right. And we know that the characteristic polynomial is LSAS plus PSBS. And we know that the closed loop poles are the zeros of the characteristic polynomial. All right. Let's look at this function here. Right. This function here is 1 plus PS on LS BS on AS, right? Which is LSAS plus PSBS divided by LSAS. So what you can see is that we have the characteristic polynomial on the top. So the zeros of the characteristic polynomial, which are the poles of the closed loop, are the zeros of this rational function, 1 plus lambda s. Okay? Given a plant and controller, we know how many poles this rational function has in the right half plane, right? Because it's just the number of open loop poles in the right half plane. For closed loop stability, we want this rational function to have no zeros in the right half plane, right? So if we could apply Cauchy's principle of the argument to this rational function, right, to determine how many zeros this has in the right half plane in excess of the number of poles it has in the right half plane. And we want, and we can determine that by evaluating this function along a contour that has as its interior the whole of the right half plane. And then mapping points along that contour under this rational function to produce a new contour, right, and counting the number of encirclements that new contour makes of the origin, which will then tell us the difference between the number of zeros of this function in the right half plane and the number of poles in the right half plane. All right? And it's in that way that we can use Cauchy's principle of the argument to assess the stability of a closed loop. Okay? So that's all summarised on this slide here. Okay? For closed loop stability, we need this rational function to have no zeros in the right half plane or on the imaginary axis for that matter. All right? We're going to get no zeros on the imaginary axis if and only if, for all frequencies, this never evaluates to -1. Okay, so that's pretty easy to check. If we just evaluate this function along the imaginary axis, then we'll get a new curve, right? Remember, this is just a complex number, right? So it'll have a real part and an imaginary part. Right, so when we're mapping points along a contour that contains the whole of the right half plane as we take this radius to infinity, we're really just plotting the corresponding complex number as a new point in the complex plane to give us a new contour, right? And we're going to count the number of encirclements that new contour makes of the origin, right, in order to determine the difference between the number of zeros of this in the right half plane and the number of poles of this in the right half plane. All right. Now, instead of mapping, so this is our contour that can be made to cover the whole of the right half plane by letting this radius go to infinity and letting these little, the radius of these little indentations go to 0. I'll explain what these are about in a minute. Okay. Instead of mapping points along here as we traverse it in a clockwise direction under 1 plus lambda and counting encirclements of the origin, what we can do is just evaluate points along here under lambda and count how many times the new contour makes encirclements of -1, right? Because the number of encirclements made by this of the origin is the number of encirclements made by this of -1, because this just shifts lambda by 1. All right? So, by Cauchy's principle of the argument, the closed loop will have z zeros in the right half plane, and that will be equal to the number of clockwise encirclements made by the contour that we get when we evaluate points along here under lambda, right? Counting those as encirclements of -1, and P is the number of right half plane poles of lambda, right? So given lambda, we know how many right half plane poles it has in the interior of this contour, right? It's the number of open loop unstable poles, right? Ultimately, we want Z to be 0, right? Because we want the closed loop to be stable. Right? The closed loop will be stable if Z is equal to 0. So the closed loop is stable if and only if the number of encirclements of -1 made by this as S traverses this so-called Nyquist D contour is equal to -P. All right? If the open loop has no unstable poles, P will be 0. And in order for the closed loop to be stable, we need the number of clockwise encirclements of -1 made by the open loop transfer function as S traverses this so-called Nyquist D contour in the clockwise direction to be 0. Right? But this is just an application of Cauchy's principle of the argument. Okay? Remember, what we're doing with Cauchy's principle of the argument is keeping track of the net change in phase of a function as we evaluate it along a contour. Right? And that's what these little indentations are about. Okay? These little indentations are around any imaginary axis poles of the open loop transfer function. Right? Yeah, we're mapping points along here under a rational function to get a new curve like these ones here. Right? If we evaluate a function that has a pole here, at that point, it's going to be a point at infinity. We can't draw it on the plot. Right? But all we're trying to do is keep track of phase. So instead of going through that point, which will push us out to infinity, we go around a little indentation so that we'll still be at a finite number, right? And as we go around here, we can still keep track of how the phase changes, right? So let's think about how the phase might change as we go around a pole of the open loop transfer function on the imaginary axis. All right? So just like in the pictures before, we can think of what we're doing here in terms of these little vectors from the pole, in this case, all right? And we're going around this curve in the clockwise direction, right? So these little vectors change in phase like this, all right? Starts off, this little vector has a phase of -π/2, right? Here it has a phase of 0, and then it goes to a phase up here of π/2, okay? So we're getting a net change in phase of this little vector of pi radians, okay? But we're saying this is a pole, right? And this little vector is just S minus j omega p, right? What we're really interested in is 1 on this, and in particular how the phase of 1 on this changes. But the phase of 1 on this, as we've seen before, is just minus the phase of this. Okay? So the net change in phase as we evaluate lambda going around here will be minus pi radians, right? So it's half a revolution in the clockwise direction. So as we mapped lambda here going at points S around here, right, we'll get a new curve in the complex plane, and that new curve will change in phase by pi minus pi radians, which is half a revolution. I've got to do half a revolution in the clockwise direction. All right? And that will be happening at points in the complex plane of large magnitude, right? Because the magnitude of lambda as we're going around here will be very large, right? Because we're close to a pole. If we evaluated it on the pole, we would be at infinity, right? And the reason we're not just going to go through the pole is so that we can keep track of the phase change, all right? And we need to do that in order to be able to properly count n, all right? So, all right, this will hopefully become clearer when we see a few examples. All right? So really what we're doing is generating the so-called Nyquist plot. The Nyquist plot is just a polar plot of the open loop transfer function evaluated around the so-called Nyquist D contour. Right? So by polar plot, I just mean we're going to plot this complex number in the complex plane as we vary S along this contour. right? So that's what the Nyquist plot is. This thing is not the Nyquist plot. This is the D contour, right? It's called a D contour because it's shaped like a D, all right? The Nyquist plot is what we get when we evaluate lambda along this contour in the clockwise direction, right? So it's this set of points, okay? In order to cover the whole of the right half plane, we're going to take the radius of this part to be very large, right? And the radius of these little indentations to be really small, okay? Now, these are just some guidelines for how to interpret a Nyquist plot once you see one, all right? So, you know, we're starting here and going up and around, right? So we're starting at omega equals 0, right? So that would be a good point to try to identify on the so-called Nyquist plot, right? Often we will be dealing with proper open loop transfer functions, and in fact strictly proper open loop transfer functions. And in the case that we're dealing with a strictly proper open loop transfer function, in other words the relative degree of lambda is a positive number, right? Then as this goes to infinity and we're evaluating around here, the magnitude is 0, okay? So often you don't see what's happening as we go around here on the Nyquist plot because it's all collapsed into 0, right? Because as we take this radius to infinity, the magnitude of lambda, if it's strictly proper, will be 0. All right? We're always dealing with real rational transfer functions for the plant and the controller, so the open loop transfer function will be real rational. And in that case, what we get when we evaluate lambda as we're moving up this part of the imaginary axis, the negative part of the imaginary axis, we'll just get the mirror image of what was obtained when moving up the positive part of the imaginary axis. All right? So that's something to bear in mind. Really, all we have to do is evaluate this most of the time along the positive imaginary axis. Okay? Because what we get around here will be 0, right? In most cases, because in most cases we're dealing with, you know, a strictly proper open loop transfer function, and then what we get here is just the mirrored image of this, mirrored in the real axis. All right? We've just seen that as you go around those little epsilon indentations, you're going to get an increase in net change in phase of minus pi radians for each pole inside the little indentation. So when you've got one pole inside the little indentation, you get a net change of minus pi. If you have 2 inside there, then you would get minus 2 pi. If you had 3, minus 3 pi, and so forth. All right? Often we're dealing with open loop transfer functions that are stable already, and we're just checking that when we close the loop that we don't lose stability for the closed loop system. And in that case, we're just trying to make sure that this set of points, the so-called Nyquist plot, does not encircle the point -1. Right? Because in order to satisfy the stability criterion in the case that P is equal to 0, we want N equal to 0. And that will correspond to keeping the Nyquist, the so-called critical point, the thing that we count encirclements around, to the left of the Nyquist plot. All right? So let's look at some examples. All right? And we're not going to stop today thinking about Nyquist analysis. We're going to continue for the whole of next week thinking about these sorts of things, so don't worry if it hasn't, sunk in yet. We'll revisit these things several times. Right? I just want to get the basic idea across today. So let's consider this as our open loop transfer function. It has 2 poles at s equals -1. Right? So that says that that tells us that the number of open loop poles in the right half plane, which we've denoted by P, is equal to 0. Right? Now, if we map points along our Nyquist D contour to new points in the complex plane under this rational function, right, then we will get this curve here. Okay? Think about what we're doing. We're starting here and we're moving up in this direction. And then we're going to move around here and then back up here until we get to our starting point. All right? So as we're moving up here, we're just really evaluating lambda at s equals j omega and increasing omega. All right? Lambda evaluated at s equals j omega is just a complex number. It has a real part and an imaginary part. As we increase omega, the real part and the imaginary parts are changing. Right? And that's what's being shown in this plot here. It's showing how the real part and imaginary part of lambda is changing as we evaluate lambda along this line. Okay? So what's happening at this point, omega equals 0? Well, you can see that omega equals 0, the imaginary part is 0, right? And the real part is 1, right? So we're at this point here. Okay? As we start increasing omega, all right, the imaginary part starts becoming negative, all right? And so we're moving in this direction, right? This direction is how the imaginary part becomes more negative, right? Which is what happens with this when we start increasing omega. So moving up here makes us move around here. All right? You can see that at omega equals 1, the real part becomes 0. Right? So that's 0 there. Right? All right? The imaginary part will not be 0. It'll be, minus 0.5 or whatever it is there. Okay? If we keep increasing omega, we end up here. Right? This is a strictly proper transfer function, has relative degree 2. All right? The magnitude of this, as we're moving around this contour, right, will be large if we've made the radius of this part of the contour large. Right? This is large S. For large S, the magnitude of this is small. And as we push the magnitude of S to infinity, by taking the radius of this part of the contour out to infinity in order to cover the whole of the right half plane, the magnitude of this becomes 0. And it's stuck at 0 the whole time we're moving around here. All right? Now we come out the other end and start moving up the imaginary axis like this. And what we get is just the mirror image of what we got when we moved up here. And sure enough, you can see that we're just getting the mirror image of what so this is what we got when we moved up here. And as we're moving up here to go back to the origin, we're getting the mirror image of that in the real axis. Okay? So this is the Nyquist plot for this. It's really just a polar plot of the open loop transfer function evaluated along the imaginary axis. All right? We have P, the number of open loop poles in the right half plane, equal to 0. How many times does this contour go around the critical point minus 1? That's what gives us n, right? So the critical point minus 1, that's minus 0.4, right? So minus 1 is over here somewhere. All right? How many times does this go around the point minus 1 in the clockwise direction? 0, right? So n is equal to 0. All right? Now, n is always equal to z minus p. So we've got z is always equal to n plus p. Z is the number of zeros of the function 1 plus lambda s, right, in the right half plane. The zeros of this are the closed loop poles. So z is the number of closed loop poles in the right half plane. And because we've got n equal to 0 and p equal to 0, we've got z equal to 0. All right, so this is telling you that when the open loop transfer function looks like this, and you close the loop around it, we will end up with a stable closed loop. Okay? Let's look at another example. So let's take now, well, let me just say one more thing about this. In terms of trying to figure out which direction you're moving in, right, it's useful to think about what the Bode plot, and in particular the phase part of the Bode plot, looks like for a function like this. All right, MATLAB puts the arrows on for you. In an exam question, I might take the arrows off and ask you to figure out what direction it goes in. The one way to do that is to use these sorts of, properties of the Nyquist plot, and to also think in terms of the Bode plot, right? Because we have rules for understanding how the phase of this changes, right, with frequency. And if you think about the phase part of the Bode plot for this, the phase part we've got two stable poles. Each of those stable poles will have phase that changes like this, right, where that's about 1 radian per second. So when we've got two of them, we get it changing like this, right? It'll go to minus pi, right? So you can see that the phase, you can't see 0 on a Bode plot, right, because it's log here, but you can see the phase is always negative, right? And it's becoming more negative, which is consistent with saying, well, we start at 0, well, that's the angle of this point here, right? And as we increase omega by evaluating lambda as we're moving along here, the phase is always decreasing towards minus pi. And in fact, as it comes in here, the angle is minus pi. It's going to minus pi. So you can understand the direction it's moving in by looking at the phase part of the Bode plot, right? Okay, let's just look at this example and then we'll finish off. All right, so let's suppose we're dealing with this as the open loop transfer function now. It has 3 poles. They're all in the left half plane, -1, -2, -3. So P, which is the number of open loop poles in the right half plane, is again equal to 0. All right. Now, this is the Bode plot that we get, right, when evaluating, the Nyquist plot obtained by evaluating this along the Nyquist contour. Okay. Again, an omega equals 0, you can see that we're going to get a number that's 20 on 1 on 6, right, which is that point there. If you look at that phase part of the Bode plot here, the phase starts at 0 and it'll head towards -3 pi on 2, right, always negative and becoming more negative. And that's consistent with moving around like this. And you can see when we zoom in here, as it's coming around, it comes in at an angle of -3 pi on 2. Right? It's consistent with what the phase part of the Bode plot would look like for a transfer function like this. All right, so it's useful to think in those terms. All right, again, it's strictly proper, so when we go around the D part, the infinite radius part of the Nyquist contour, we get stuck at 0. Then we come out the other end, we get the mirror image. Okay. Now, how many clockwise encirclements of the critical point? -1 do we get? Well, we get none. Right? So n is equal to 0. And so we get z, which is n plus p, equal to 0. So if we grab this transfer function and close the loop around it, we'll get a stable closed loop. Let's think about this situation. We'll put a constant gain here when closing the loop. Okay? What's that going to do to the Nyquist plot if we assume, say, that k is a positive number? Well, it's not going to change the phase of this, right? But it's going to change the magnitude. So if we look at what's going to happen, this point corresponds to a particular frequency. If we now multiply lambda by k, it's going to push that point this way if k is bigger than 1, and this way if k is less than 1. Right? It doesn't change the phase. Right? So if this is lambda at j omega, right, then this will be k lambda j omega for k bigger than 1, and this would be k lambda j omega for k less than 1. It just moves along the ray, right? Because the phase of this is 0, so it doesn't change the phase. So multiplying lambda by a constant gain just stretches or shrinks the Nyquist plot without rotating it at all in the complex plane, and it stretches it out if the gain is bigger than 1 and shrinks it if the gain is less than 1. All right? So let's see what would happen if we grabbed this Nyquist plot, right, like this, and multiplied it by a gain bigger than 1. Then all these points would stretch out. You know, this point would stretch out to there, this point would stretch out by the same amount, right, to there. This point would stretch out. And if we make it stretch out far enough, it's like putting the critical point inside that little loop. Right? So if we multiply by a gain bigger than 1, we can end up, by making that gain sufficiently large, stretching that point out there so that the critical point ends up in the middle. And for that case, we would get 1, 2 clockwise encirclements of the critical point. So our n would become 2, and we would end up with 2 unstable closed-loop poles, right? In the case that we have this transfer function multiplied by a gain big enough to shift the critical point inside that little loop. And that's consistent with what we would get if you think about the root locus plot. We have a relative degree 3 system, right? So we know that'll be part of the root locus, that'll be part of the root locus. As we increase k, these points start moving together. This one just moves towards minus infinity. As these meet, they come apart, right? And they go to asymptotes. The asymptotes, because we have a relative degree thing, will be things that go off at an angle, like this, right? And for sufficiently large k, we end up with 2 closed-loop poles in the right half plane, right? Which is precisely what's predicted by the analysis in terms of the Nyquist plot. Okay, so this is just another tool, just like root locus is another tool that can be used to inform design decisions. There's a lot of information in these plots. All right, so next time we'll continue looking at more examples of these things.
How to do just substitute the
S equals J omega. Yeah.
but I substitute S with J omega and I cannot get.
Right.
Yeah.
Okay. And so,
Just omega plus J omega plus.
well, hang on, let me just think. Right.